Hi everyone, welcome to Chem Help ASAP. We are going to be working the Chapter 1 problems in the Open Stax Atoms First textbook. Now we will do both the example and the check your learning problems in this chapter. Let's get started with example 1.1. So this is the calculation of density. First, I'll just read through the problem. Gold in bricks, bars, and coins has been a form of currency for centuries. In order to swindle people into paying for a brick of gold without actually investing in a brick of gold, people have considered filling the centers of hollow gold bricks with lead to fool buyers into thinking that the entire brick is gold. It does not work. Lead is a dense substance, but its density is not as great as that of gold, 19.3 grams per centimeter cubed. What is the density of lead if a cube of lead has an edge length of 2 centimeters and a mass of 90.7 grams? All right, so let's get started. To calculate density, we need the mass of the object and the volume of the object. So density equals mass over volume. We have the mass of our lead brick, 90.7 grams, but we are lacking the volume. What other information do we have that can maybe help us determine a volume? Well, we know we have a cube, and we also know the length of one edge. So if you think of a three-dimensional cube, all of the edges here are going to have a length of 2.00 centimeters. If you remember from geometry class, the volume of a cube is the length times the width times the height. And for our cube, of course, all of these values are the same. They are all 2.00 centimeters. So my volume for this cube is 8.00 centimeters cubed. So notice that not only do your numbers multiply, but also your units. I have centimeters times centimeters times centimeters. That's where the centimeters cubed comes from. And it makes sense because we have a volume, so we should have centimeters cubed. Now I have a volume along with my mass given by the problem, so I can calculate the density. So my density is simply going to be my mass, which is 90.7 grams, divided by my volume, which is 8.00 centimeter cubed, which gives me a density of 11.3 grams per centimeter cubed. Now let's work the check your learning problem. So this problem is very similar. Part A asks to 3 decimal places what is the volume of a cube with an edge length of 0.843 centimeters. And then part B says if the cube in part A is copper and has a mass of 5.34 grams, what is the density of copper to 2 decimal places? All right, let's work this problem. Again, we have a cube. So the length of all of our edges is going to be the same. And in this case, we have an edge length of 0.843. And that is centimeters. So our volume, again, is length times width times height, which is the same for all of these. So my volume is equal to 0.599, again, centimeters cubed. So that is part A done. Let's take a look at part B. Now we're going to calculate the density. Again, remember for density, we're going to have the mass of the object over the volume. And in this case, we are given the mass as 5.34 grams. We just calculated the volume, and that is 0.599 centimeters cubed. So our density is 8 1.91 grams per centimeter cubed. On to example 1.2. We are using displacement of water to determine density. So we are going to use a simulation to illustrate an alternative approach to the determination of density that involves measuring the object's volume via displacement of water. Use a simulator to determine the densities of both iron and wood. So let's head over to that simulation. Okay, here we are in our simulator. And the first thing that I am going to do is I want to make sure that this is water in here. You can see I can alter my fluid density, and water has a density of 1 gram per milliliter, so this is not correct. So I'm just simply going to click turn fluid into water, and then you can see I'm automatically back at 1 gram per milliliter. Now, the first object that we have to measure is iron. So I'm going to click on iron down here. So now I have my iron bar. Let's get a mass. All right, so the mass of my iron bar here is 31.48 grams. And now I need to figure out the volume. So there are two numbers that I want to record. I first want to record my volume just here of the fluid with nothing in it. That is 25.5. And then I want to record the volume of the water once I put my iron bar in, and that is 29.5. Okay, so that is all the data we need to calculate the density of iron. Let's go ahead and gather our data for calculating the density of wood. So I am going to change this over to wood. You can see it floats. Okay, so come here, piece of wood. Let's get a mass. All right, so the mass of our piece of wood is 1.95 grams. Again, you can see our initial volume here of our water is 25.5, so I want to make sure I have that. And now if I put the wood in, now what I want to do, because the wood floats and you can see my volume is changing there, so I actually want to pull the wood down a little bit. So my final volume is actually 28.5. That is actually the volume of the piece of wood. I don't want to record anything when it's floating. Okay, so we have everything we need from the simulator. Now let's go back to our page and let's do our calculations. So let's write down the data we collected. For the iron, we had a mass of 31.48 grams. And our final volume of our water was 29.5 milliliters. And our initial volume of our water before we put the chunk of iron in was 25.5 milliliters. Remember, for density, we need mass over volume. Well, we have the mass, that's pretty straightforward, but our volume is not 25.5 or 29.5, but the difference between those volumes. So the volume of our iron bar is going to be our final volume minus our initial volume, and that is simply 29.5 milliliters minus 25.5 milliliters. So our volume of our iron is 4.0 milliliters. Now I can plug into my density. Again, my mass is 31.48 grams. My volume is 4.0 milliliters. So the density of iron is 7.87 grams per milliliter. So my final answer should actually only have 2 sig figs. So my final density should be 7.9 grams per milliliter. Let's do the same thing for our wood. Again, the mass of my piece of wood was 1.95 grams. My final volume, when I dropped my piece of wood in, was 28.5 milliliters, and my initial volume was the same, 25.5 milliliters. Okay, so the volume of my piece of wood, of course, is the same as I did for the iron. The final volume minus the initial volume, this is 28.5 milliliters minus 25.5 milliliters. So the volume of my piece of wood is 3.0 milliliters. Now to calculate the density, of course, density is simply mass over volume. So this is going to be 1.95 grams divided by 3.0 milliliters. So my density is 0.65 grams per milliliter. Let's take a look at the check your learning exercise. All right, we're still going to use the water displacement approach. So we're using the simulator, and this time we are collecting information about the foam sample. So let's go back to the simulator and take a look at the foam sample. So we still have our piece of wood floating in here, so I'm just going to pull that out. And let's change this to foam. There we go. And we already have our mass. That's great. So the mass of our foam is 2.76 grams. Again, make sure you record this initial volume here. This is 25.5. Let's drop our foam in. And just like the wood, it's going to float. So we want to make sure that we hold it down and we get that proper final volume. So let me just grab it, pull it down. So that is 37.5 milliliters. That is all the data we need for our foam. So let's go back and do our calculations. Okay, so here is the data we got for our foam. The mass of our block of foam was 2.76 grams. Our final volume was 37.5 milliliters. And just like with all of the other parts, our initial volume was 25.5 milliliters. Okay, let's calculate the volume of our block of foam. Of course, we're going to take our final volume. We're going to subtract our initial volume. And so the volume of our block of foam is 12 milliliters. Now for density, we're simply going to take our mass over our volume. The mass of our block of foam was 2.76 grams, and the volume we just calculated was 12.0 milliliters. So the density of our foam is 0.23 grams per milliliter. For reasons that will become obvious when we learn about significant figures, we actually need 3 sig figs for this density, 0.230 grams per milliliter. That is density, and that now gives us 3 sig figs for our answer. Okay, great. Let's go on to our next problem. Example 1.3, we are going to be rounding numbers. So we're going to round to the indicated number of sig figs or significant figures. So we'll take each one of these in turn here. Let's start with A. So we have 31.57 and we want to round to 2 sig figs. That means I'm going to round to the ones place. And so what I need to do is I need to look at the place just to the right of where I want to round, and that is a 5. So remember, the 5s are tricky. So I need to also look at what is to the right of the 5 and know if that is a 0 or a non-zero. Because it is a non-zero, it's a 7. That means we are going to round up. So this 31.57 becomes 32, and that has 2 sig figs. All right, let's take a look at problem B. We have 8.1649, and we want to round this to 3 sig figs. So I am going to be rounding to the hundredths place right here. So I want to look to the right. That is less than 5, so it is going to round down. So this becomes 8.16, and that has 3 sig figs. Okay, part C, we have 0.051065 We want to round this to 4 sig figs. So 1, 2, 3, 4. I am rounding the 6 there. To the right of the 6 is the 5, so I need to use my rules for 5s. Now there is nothing after the 5, so we treat this as if there were zeros after the 5. Now what that means is we want to round this 6 or this place so that it is an even number. Well, it's already an even number. It is a 6, so we just keep it a 6. This is often called rounding down, although for me it works better to think of just keeping the even digit. So whatever works for you, whatever makes the most sense, use that. So that number is now rounded to 4 sig figs. Okay, part D, we have 0.90275, and we are also going to round this to 4 sig figs, so 1, 2, 3, 4. So we are rounding right there where that 7 is. So we have a 5 immediately to the right, and just like in part C, there is nothing after the 5. So we want to round this so it has an even digit, which means we are going to round up. So this number becomes 0.9028 because we bumped this 7 up to an 8, and now we have 4 sig figs. Let's go on to the check your learning problem. So again, we are rounding to the indicated number of sig figs. So for A, we have 0.424, and we are going to round to 2 sig figs, so 1, 2. So we're rounding this 2 here. There's a 4 afterwards, so we do not round up. We keep everything. So that rounds to 0.42. Okay, part B, we have 0.0038661. We are rounding to 3 sig figs, so 1, 2, 3. We are rounding this first 6 here. So immediately to the right is a 6. This means we round up. So rounding here will give us 0.00387. And that again, that has 3 sig figs. Part C, we have 421.25, and we are rounding to 4 sig figs. So 1, 2, 3. We're rounding this 2 right here. Now, there is a 5 afterwards, so we're going to use our rules for 5s. Now, there is nothing after the 5, so we treat it like it's got a bunch of zeros. That means we need an even number. Well, 2 is already even, so we just keep it. So this rounds to 421.2, and that again has 4 sig figs. And last, part D, this is 28,683.5, and we want to round to 5 sig figs, so 1, 2, 3, 4. So we're going to round to this 3 right here. There is a 5 to the right, so we're going to use our rules of 5. There is nothing after the 5, so we're going to pretend like there are zeros and use that rule. So what we want to do is we want to make this 3 even, which means we are going to round up. And this is going to become 28,684. And again, this has 5 sig figs. On to example 1.4. So we're going to practice our rules here. So we're doing addition and subtraction with significant figures. So they give us just the reminder of the rule. When adding or subtracting numbers, round the result to the same number of decimal places as the number with the fewest decimal places, i.e. the least certain value in terms of addition and subtraction. So we are going to be counting up decimal places. For part A, I find it easiest to put my numbers, if I can, one on top of the other. Sometimes you can do this and sometimes you can't. Oops, I forgot my grams there. So we are going to add these two numbers. Let's go ahead and just add them, and then we will round to the correct number of significant figures. So if I just add these two together, I get 5.3853. And and that is grams. Now let's determine significant figures. So again, addition, subtraction, just like the rule reminded us, we're looking at numbers of decimal places. So my first number here has 4 decimal places and my second number has 3 decimal places. Well, the number with 3 decimal places is going to limit my answer, and specifically it is going to limit my answer to 3 decimal places. So 3 decimal places here means I'm going to round at that 5. Because there is a 3 to the right of that 5, that means my answer is actually 5.385 grams. And that is my final answer with the correct number of sig figs. Part B, we are going to subtract 421.23 from 486. Again, I'm going to line these up just because it helps me. And I am subtracting here. So again, I'm just going to write down what my calculator shows, and it gives me 64.77. I'm sorry, both of these are grams. I don't mean to drop my units there. Now I'm going to decide on rounding. So my first number here has no decimal places, or is just rounded to the ones place. And my second number gives me 2 decimal places. So this first number, this 486, is going to limit my number of decimal places, which means I need to round my answer to the ones place, or I'm going to round my answer right here at this 4. Now there is a 7 immediately to the right of the 4, so this is going to be rounded up. So my final answer is 65 grams. On to the check your learning problems. Here we have more addition and subtraction. So for part A, we are going to add these 2 numbers. And we're going to add 0.31 milliliters to that. Again, I like to line it up. This is addition. So this is what my calculator gives me. Now let's round that to the correct number of sig figs. So again, I'm looking at decimal places. So my first number here has 3 decimal places. My second number has 2. So my answer must also have 2 decimal places, which means I'm rounding at this 4 right here. There is a 4 to the right, so I'm going to round down. So my final answer is 2.64 milliliters. For part B, I'm back to subtraction, so I'm going to subtract these 2. Again, I'm going to line these up, and I'm subtracting 55.8752 meters. Subtract. Here is the answer that my calculator gives me. Now let's determine where to round. So my top number here has 3 decimal places. My bottom number has 4. So I'm going to round to 3 decimal places, which means I am rounding this 7 right here. I have an 8 immediately to the right, so this is going to round up. So my final answer is 0.658 meters. Example 1.5. Now we're going to practice multiplication division. So they remind us of the rule: when multiplying or dividing numbers, round the result to the same number of digits as the number with the fewest significant figures, the least certain value in terms of multiplication and division. So in addition, subtraction, of course, we looked at decimal places. This time we're just going to look at the number of sig figs in all of the numbers that we're multiplying and dividing. So for part A, we are multiplying these 2 numbers. 6238 centimeters multiplied by 6.6 centimeters. So my calculator gives me 4.11708, and that would be centimeters squares because my units get multiplied as well. So now in terms of sig figs, so I'm looking at total sig figs. So this first number here has a total of 4 sig figs. My second number only has 2. So my answer must be rounded to 2 sig figs, which means I am going to round to this first one. Now there's a 1 immediately to the right, so I'm going to round down. So my final answer is 4.1 centimeters squared. Okay, part B, I am doing division. So I have 421.23 grams divided by 486 milliliters. This is actually a density calculation. So when I do this division, my calculator gives me a whole slew of numbers. I'm not going to write all of them out. This goes on for quite a while. I'm just going to write out enough that I know I can round to the correct decimal place. And my units here are going to be grams per milliliter. So my numerator has 1, 2, 3, 4, 5 sig figs, and my denominator only has 3. So my denominator limits me. My answer should have 3 sig figs, so that means I'm going to round at this 6 right here. So immediately to the right of this 6 is a 7, so I'm going to round up. So my final answer is 0.867 grams per milliliter. On to the check your learning. So again, we're doing multiplication and division here. So for part A, we are multiplying 2.334 centimeters times 0.320 centimeters. So again, I'm just going to write what my calculator gives me. And that gives me 0.74688. And my units will be centimeters squared. So let's determine how many sig figs I need. So my first number here has 4 sig figs, and my second number only has 3. So my answer is going to be limited to 3 sig figs, which means I need to round this 6 right here. Immediately to the right of my 6 is an 8, so I'm going to round up. So this becomes 0.747 centimeters squared. Okay, great. Let's go on to part B. Now I'm dividing again. So I have 55.8752 meters divided by 56.53 seconds. This is actually going to give me a velocity. Again, when I put this in my calculator, I get 0.988. Okay, I'm going to get a lot of digits here. So I'm not going to write them all out because that should give me enough. This is meters per second. Okay, now let's determine our significant figures. So my numerator here has 1, 2, 3, 4, 5, 6 significant figures. My denominator has 1, 2, 3, 4. So I'm going to be limited by my denominator. I'm going to have 4 significant figures, 1, 2, 3, 4. So I need to round at this 4 right here. Immediately to the right of that 4 is a 1, so I am going to round down. So this rounds to 0.9984 meters per second. Example 1.6, calculation with significant figures. Okay, so one common bathtub is 13.44 decimeters long, 5.920 decimeters wide, and 2.54 decimeters deep. Assume that the tub is rectangular and calculate its approximate volume in liters. Okay, so the volume of a rectangular solid is going to be length times width times height. Although really you could think of height in this case as depth. It's going to be the same thing. We just need to multiply all of these dimensions together. So I am going to have 13.44 decimeters times 5.920 decimeters times 2.54 decimeters. Okay, let's just get this in our calculator. So multiplying this gives me 202.0945. A lot of numbers. I know that I shouldn't be keeping all of these numbers. And of course, my units are going to be decimeters cubed here. So let's determine sig figs. Multiplication, division. I am looking at total number of sig figs. So I have 4 sig figs in my first number. I'm just going to write a little 4 above here so I can keep track. I have 1, 2, 3. I also have 4 sig figs here, and I have 3 sig figs here. So I'm going to be limited by this last number here. It only has 3 sig figs, which means my answer should have 3 sig figs. So I need to round to this ones place right here. There is a 0 immediately to the right of my 2, so my volume will round down. This is simply 202 decimeters cubed. And just as a side note, decimeters cubed is actually liters. This is why they want the approximate volume in liters. So I can simply rewrite this as 202 liters. Now on to the check your learning calculation. We are doing a density calculation. What is the density of a liquid with mass of 31.1415 grams and a volume of 30.13 centimeters cubed? All right, so of course density is simply mass over volume. So let's put our numbers in here. So we have 31.1415 grams and divided by 30.13 centimeters cubed. All right, first let's just do the calculation. So my calculator gives me quite a few numbers. Again, I probably didn't need to write down all of those, but that's all right. Now let's determine sig figs. Okay, because I've got a lot of digits here, I'm going to write on top. So my numerator has 1, 2, 3, 4, 5, 6. I'm just going to put a little 6 up here, and my denominator has 4. So I'm going to be limited to 4 sig figs. So 1, 2, 3, 4. I'm going to round at this second 3 here. Now after the 3 is a 5, so I have to use my rules of 5. And after the 5, I have a bunch of digits. I've actually got a 7 here, so I am going to be rounding up. So my final answer for my density is going to be 1.034 grams per centimeter cubed. Example 1.7, we get a picture with this one. So again, we're calculating density using water displacement, except we're not going to use a simulator. A piece of rebar is weighed and then submerged in a graduated cylinder partially filled with water with results as shown. So you can see here is the graduated cylinder without the rebar, and here is a graduated cylinder with the rebar, and they actually give us all of our volumes and our mass. Okay, so for part A, we want to use these values to determine the density of this piece of rebar. And for part B, it says rebar is mostly iron. Does your result in A support this statement, and how? Okay, so let's first just calculate the density of this rebar. Okay, for part A, as we know, density is mass over volume. Well, we have the mass, but we're going to need to calculate the volume first. So remember, the volume for our piece of rebar is going to be our final volume minus our initial volume. Now, in this case, it's great that they go ahead and give this to us. So we have 22.4 milliliters minus 13.5 milliliters. That gives us a volume of 8.9 milliliters. Let's check our sig figs here. So we're doing subtraction here. We're looking at decimal places. Each of these numbers have 1 decimal place, so my answer should also have 1 decimal place, and you can see that it does. So my volume is rounded to the correct number of significant figures. Now let's calculate our density. We have our mass over here, 69.658 grams over 8.9 milliliters. So our density, we've got a lot of decimal places here. Okay, so I'm just going to stop with that one because that should give us enough. Now let's round to the correct number of significant figures. All right, so my numerator here has 1, 2, 3, 4, 5 sig figs, and my denominator only has 2. So my answer needs to have just 2 sig figs because my denominator limits. So that means I need to round to this 8 right here. There's a 2 after the 8, so I'm just going to round down. So 7.8 grams per milliliter. All right, so that is our calculation for part A. Now let's look at part B. Okay, so rebar is mostly iron, so does this support this statement? Well, we need to know the density of iron. So if you look in your text, you can find there's a table that gives you a lot of densities, and they actually give the density of iron as being 7.9. 0.9 grams per milliliter. So yes, this is almost exactly the same density that they give in your textbook, which means that rebar, or at least this piece of rebar, is going to be mostly iron. On to the check your learning. Again, we're going to do the same thing. We've got a mass and we've got our two volumes. All right, so part A, use these values to determine the density of the material. And then in part B, do you have any reasonable guess as to the identity of this material, and explain your reasoning? Well, let's just get part A done first. Density is mass over volume, but just like we did in the previous problem, we need to use these volumes to calculate the volume of our lump of whatever this is. So the volume of our unknown piece of metal is going to be our final volume minus our initial volume. So this is going to be 19.8 milliliters minus 17.1 milliliters. Okay, putting this into my calculator, I get 2.7 milliliters. Let's check our sig figs. Both of our volumes have one decimal place because we're doing subtraction here, so we're looking at decimal places, so our answer should have one decimal place. That's perfect. Now to calculate our density, we have our mass over here as 51.842 grams over the volume we just calculated. So density is got a lot of decimal places here. I'm just going to put these down. This should give us enough. Now let's round to the correct number of sig figs. Okay, so my numerator has 1, 2, 3, 4, 5 sig figs, and my denominator only has 2. So I need 2 sig figs in my answer, which means I am rounding to that 9. So my density is going to be just 19 grams per milliliter. Okay, so that is part A finished. Let's take a look at part B. So this is, we're going to guess the identity of this material. Again, if you go to your textbook and you look at the table of the different densities of different metals, then what you're going to find is the density of gold is listed as 19.3 grams per milliliter, or grams per centimeter cubed. And so that would lead us to believe that this metal is gold. It's also shiny and yellowish, as well as having just about the exact density of gold. On to example 1.8. We are now practicing conversions. The mass of a competition frisbee is 125 grams. Convert its mass to ounces using the unit conversion factor derived from the relationship 1 ounce equals 28.349 grams. So we can also use table 1.6 as well for all of our conversion factors. Okay, so we have a frisbee that is 125 grams. What we need to do is we need to set up our conversion factor such that our grams cancels and we're left with ounces in the numerator. So I am going to multiply this by 1 ounce over 28.349 grams. Now, the reason why this works is this ratio here is actually equal to 1 because 1 ounce equals this many grams. These are equivalent, hence the equal sign here. So all we're doing is we're taking our original mass and we are multiplying by 1. This is how conversions work. Now, we want to be really careful when we do this that our units cancel. So I'm going to switch colors here. And I want you to see how my grams cancel, and then I have ounces here in the numerator. That's exactly what I want. So if you're doing these conversions and you accidentally flip-flop this conversion factor and you put grams in the numerator, hopefully the thing you notice is that the units you want to get rid of are not canceling, and you're also left with units that you do not want in the denominator. Okay, so now that we're confident that we have this conversion set up correctly, let's actually put it into our calculator. So this is going to give us 4.4, a lot of decimal places, and that is now ounces. Let's go ahead and get the correct number of sig figs. All right, so this is multiplication division. We do assume that this 1 here is exact by the very definition, so that does not limit us. Our 125, of course, has 3 sig figs, and our 28.349, that has 5 sig figs. So we're going to be limited to 3 sig figs for our answer, which means we need to round to that 0 right there. So there is a 9 immediately to the right of that 0, which means we are going to round up. So my final answer is 4.41 ounces. On to the check your learning. We are going to convert a volume of 9.345 quarts to liters. Again, we want to use the conversion factors that are given in your textbook for this. So we have 9.345 quarts, and we're going to go all the way to liters. So I know that 1 quart is 0.94635 liters. So I want to write this conversion factor such that my quarts are in the denominator and my liters are in the numerator. So this is 1 quart is 0.94635 liters. Again, you can see that my quarts cancel and I am left with liters, which is where I want to be. When you're first starting conversions, I always found it helpful to actually put my units in first and then put the numbers in. So I get 8.84364 and lots of decimal places here. Let's go ahead and round to the correct number of sig figs. So my first number here has 4 sig figs. Again, this one is exact. And I have 5 sig figs in my conversion factor. So my initial number is going to limit me. I should have 4 sig figs in my final answer. So 1, 2, 3, 4. I'm going to round to this 3. And there is a 6 immediately to the right, which means I'm going to round up. So my final answer is 8.844 liters. Example 1.9, computing quantities from measurement results in known mathematical relations. What is the density of common antifreeze in units of grams per milliliter? A 4-quart sample of the antifreeze weighs 9.62 pounds. So there are a couple of different ways to approach this problem. I am going to show you 2 different ways to approach this problem, but as you do more and more of these conversions, you're going to kind of find the way that you are most comfortable with. So let's start with basically our 2-step process, and let's convert each of these, our volume and our mass, to the units that we want. So we have a mass of 9.26 pounds. Now the problem asked us for grams per milliliter, so we need to take this pounds into grams. Okay, so I know that there are 453.59 grams in 1 pound. Again, these conversion factors are available in your book. And that gives me 4,200.2434 grams. Okay, let's get this rounded to the correct number of sig figs. My 9.26 has 3 sig figs. Again, this one is exact, and I have 5 sig figs in my conversion factor, so I'm going to round to 3 sig figs, which means I am going to round to the tens place right here. So this is going to round to 4,200 grams. Now there are 2 different ways that you can handle this. You can either put a line under that 0 just to remind yourself, hey, that 0 is significant and I'm going to carry this forward, and I just want to remember how many sig figs in this number. We are actually going to carry this number forward, so this would be something that maybe I would do. However, if you are trying to report this number to 3 sig figs, you would need to convert this into scientific notation, and that would be 4.20 times 10 to the 3rd grams. This number now has 3 sig figs, whereas this number really only has 2 sig figs. So it really just depends on your situation if you want to convert to scientific notation or not. So that is converting our pounds into grams. Now let's convert our quarts into milliliters. So I have 4.00 quarts, and my conversion factor here is 1 liter over 1.0567 quarts. Again, notice my quarts are canceling here. And now I have liters, except I want milliliters, so I need one more conversion factor. And there are 1,000 milliliters in 1 liter. So this is actually a sequence of 2 conversion factors. Now, if I put this in my calculator, I get a lot of numbers out. All right, I'm going to end there. That should give me plenty to work with. So let's determine sig figs. All right, so I started with 3 sig figs here. Again, that one is exact, and I have 1, 2, 3, 4, 5 sig figs here. Now, this conversion factor here is an exact conversion factor. Again, whenever you have an exact conversion factor, it has an infinite number of sig figs, so it will never, ever limit you. By definition, 1 liter contains exactly 1,000 milliliters. So you could think of even just this 1,000 as having an infinite number of zeros after it. Okay, so I'm going to be limited by my 4.00 quarts. I need 3 sig figs in my answer, which means I'm going to round to this 8 right here. There is a 5 immediately to the right of the 8, so I'm going to use my rules of 5s. And there are numbers afterwards. They're not zeros or no numbers. So what I'm going to do is I want to make sure that I have an even number to the left of the 5. The 8 is already even, so I am just going to keep it. So this is going to round to 3,780 milliliters. Now to calculate my density, of course, is just mass divided by volume. So in my case, I have my 4.20 times 10 to the third grams over 3,780 milliliters. And that gives me 1.11 grams per milliliter. Let's double check our sig figs on this last part. So my numerator has 3 sig figs. My denominator also has 3 sig figs. So my answer should have 3. And yes, my answer has 3 sig figs. So this is the answer with the correct number of significant figures. Now, as you get more comfortable with these conversions, you're going to want to put as many of these calculations together as you can. So let me show you a different way of doing this calculation where you can avoid having multiple steps. So I am going to start with my formula of density equals mass over volume. And I'm going to start with my original units here. So I have my 9.26 pounds divided by 4.00 quarts. And I'm just going to take it in turn to convert these to the units that I want. So when I do these long conversions, instead of multiplying like I've done up here, I use a technique that I call fence posts. And so I'm just going to create a long strand here of different conversion factors. So first, I'm going to take care of my pounds and convert that into grams. So I know that I want pound in the denominator here so that I get cancellation. Well, 1 pound equals 453.59 grams. And you can see what this does is it allows the pounds to cancel, and then I'm left with grams, which is exactly what I want. So my mass has been changed. Now I'm going to deal with the quarts. I know I want my quarts here to cancel, which means I need my quart unit to be in the numerator and my liters to be in the denominator. So there are 1.0567 quarts in 1 liter. Again, just to show the units canceling, my quarts cancel, and I am left with liters. But of course, I'm going to milliliters, so I am not done with my conversion factors yet. In 1 liter, there are 1,000 milliliters. Sorry, that is a comma. Again, what I want to show here is that my liters have canceled, and now I'm left with milliliters. So if I'm just looking at my units, you can see that I have grams per milliliters, which is exactly what I want here. So in these type of problems, I like to say, let your units lead you. It will tell you what kind of calculation you need to do, whether you need to multiply or divide. So now what I have is just one long calculation, but it will get me to my final answer. So if I put all this into my calculator, what I get is 1.109599. It keeps going. Grams per milliliter. So now I have my answer. I just need to round to the correct number of sig figs. So I need to go back and look at everything I used and determine my sig figs. So my 9.26 has 3 sig figs. My 4.00 also has 3 sig figs. Up here I have 5 sig figs. This one has 1, 2, 3, 4, also has 5 sig figs. And of course my 1000 milliliters in a liter has an infinite number of sig figs. So what I am limited by are both my pounds and my quarts. So my final answer should have 3 sig figs, which means I am rounding to that 0 right there, which you can already see is going to give me an answer of 1.11 grams per milliliter, which is exactly what we got when we did it the other way. So both of these methods absolutely work. Use the one that makes the most sense to you. Now for the check your learning. What is the volume in liters of 1 ounce, given that 1 liter is 1.0567 quarts and 1 quart is 32 ounces exactly? All right, so we're just going to string along some conversions so that we end up with the units that we want. So we have 1.000 ounces. Again, I like to use my fence posts. So first what I want to do is I want to get rid of my ounces. So I have 2 conversion factors here, and the one I want to use first is this 1 quart equals 32 ounces because I'm looking to get rid of this ounces. So I want to make sure my ounces are in the denominator and my quarts are in the numerator. And so this is 1 quart and 32 ounces. Now I want to take my quarts and use my second conversion factor and get that to liters. So I want to make sure that my quarts cancel. So that's going to go in the denominator, and that means my liters go in the numerator. So that's 1 liter and 1.0567 quarts. Okay, so before I run this calculation, let's make sure everything cancels like I want. So yes, ounces are canceling. Quarts are canceling. I'm left with liters, which is exactly what I wanted. Okay, so I put this in my calculator, and of course I get a lot of decimal places that come out here. All right, that should be enough for us to go on, and that is liters. So let's determine sig figs. So I started with my 1 ounce, and this has 4 sig figs. Now my 1 quart is 32 ounces. You can see that they specified that as exact. So that means this has an infinite number of sig figs. And then this conversion factor has 1, 2, 3, 4, 5 sig figs. So it looks like I'm limited with my starting number, so I should have 4 sig figs. So 1, 2, 3, 4. I need to round at that 7 right there. I have a 3 afterwards, so I'm just going to keep that 7. So my final answer is 0.02957, and that is liters. Now, one thing I want to point out is in the textbook, this last digit is not a 7. I believe it's actually a 6. I am not completely sure how they got a 6 here, but the important thing is you've set up your conversions properly and you have rounded to the correct number of sig figs. As you continue on in chemistry, you will find that you and the person next to you, especially if you're doing a long calculation, might get an answer that is just a little bit off. This is really not something to worry about. When you're doing that many calculations in a row, then a lot of times you can end up with something called rounding error, which hopefully remains very small and is usually not a problem. Example 1.10, computing quantities from measurement results and known mathematical relations. So while being driven from Philadelphia to Atlanta, a distance of about 1,250 kilometers, a 2014 Lamborghini Aventador Roadster uses 213 liters of gasoline. I'm sorry if I have butchered that name. I am not a car person. Okay, so part A asks what average fuel economy and miles per gallon did the Roadster get during this trip? And if gasoline costs $3.80 per gallon, what is the fuel cost for this trip? There are two different ways to approach part A. So I'm going to start with breaking part A up into two different calculations, and then I'll show you how you can put it all together in one calculation. Let's start with our distance. That is 1250 kilometers. So what we're aiming for is miles here. So I want my kilometers to cancel, and this is 0.62137 miles. Again, I'm using the conversion factors that are given in the book here. So that is going to give me 777 miles. Now let's double check and make sure I had the right number of sig figs. This first number here has 3 sig figs. My conversion factor has 5 sig figs, so I should have 3 sig figs in the answer, and that is how many I have. Just as a quick side note, when using these conversions, your conversion factor should always have more significant figures than the number you started with. You never want your conversion factors to actually limit your answer. You want your measurements to limit your answer. So that is kilometers changed to miles. Let's go ahead and change our liters here into gallons. So I have 213 liters. Again, I am using the conversion factors found in your textbook. I want my liters to cancel, so I'm going to first convert it to quarts. 7 quarts. And of course, there are 4 quarts in 1 gallon exactly. Okay, so this is going to give me 56.3 gallons. Again, double check my sig figs. So I started with 213 liters. That has 3 sig figs. This conversion factor has 5 sig figs. And this is another exact conversion factor. By definition, there are exactly 4 quarts in 1 gallon. So this will not limit me, which means my starting measurement limits me, which is exactly what I want. It's got 3 sig figs. So you can see that is why I have 3 sig figs in my answer here. Now I'm going to calculate my fuel economy in miles per gallon, or miles divided by gallon. So that is simply going to be 777 miles divided by 56.3 gallons, which gives me a fuel economy of 13.8 miles per gallon, or 13.8 mpg, just depending on how you like to write it. Double check my sig figs. So my numerator has 3 sig figs. My denominator also has 3 sig figs, so that is why my answer has 3 sig figs. Okay, but what if I wanted to do this calculation just in one go and not split it up into 2 parts? All right, here we go. I would start with my 1,250 kilometers because I want my distance in the numerator. And this is over my volume, which is 213 liters. Now you can change these units in whatever order you want. I'm going to first deal with my kilometers, and then I'm going to deal with my liters. But if you wanted to, you could convert your liters first and then deal with your kilometers. That's the beauty of multiplication division, is it can be done in whatever order makes the most sense to you. Okay, so first I'm going to convert to miles. So in 1 kilometer, there are 0.62137 miles. So that is my distance taken care of. Now I'm going to take care of my liters. So in 1 liter, there are 1.0567 quarts. And then, of course, I need to convert quarts into gallons. So there are 4 quarts in 1 gallon exactly. And this also gives me my 13.8 miles per gallon. But let's double check. Just want to make sure that you can see how this works. So you can see my kilometers canceled, and that's how I get miles in the numerator. My liters have canceled, my quarts have canceled, and I have gallons in the denominator. Now, to check for sig figs, we're just going to look at all of these conversion factors. So again, my numerator here has 3 sig figs, and my denominator also has 3 sig figs. This conversion factor has 1, 2, 3, 4, 5 sig figs. This one has 1, 2, 3, 4, also 5 sig figs. And of course, this is an exact conversion, so it's infinite. So you can see why I should have 3 sig figs here, because here in both my numerator and denominator, I have 3 sig figs. That is part A. Let's take a look at part B. Okay, I am going to squeeze part B into this little space here. So we know what gasoline costs, and we want to know our total fuel cost for the trip. So what I need to do is I need to take my cost per gallon and multiply by how many gallons I use. This is where it comes in handy to have done the 2-part problem, because I know that I use 56.3 gallons, and I'm going to multiply that by $3.80 per gallon, and that gives me $214. So let's check our sig figs. We have 3 sig figs here for our 56.3. This also has 3 sig figs, so you can see my answer does have 3 significant figures. You can also see that my units cancel, my gallons cancel here, which leaves me with dollars in the numerator, which is exactly what I wanted. Now for the check your learning. A Toyota Prius hybrid uses 59.7 liters of gasoline to drive from San Francisco to Seattle, a distance of 1,300 kilometers. And they're telling us specifically that this has 2 sig figs. So part A asks, what average fuel economy and miles per gallon did the Prius get during the trip? And part B says, if gasoline costs $3.90 per gallon, what was the fuel cost for this trip? So we will first do part A broken up into 2 steps, and then we'll show it in 1 step. Let's first convert our 59.7 liters into gallons. So it did ask us for gallons here. Again, using the conversion factors that are found in your textbook, I am first converting to quarts, and then I'll take quarts, that is a Q, into gallons. Okay, so that gives me 15.8 gallons. Let's make sure our sig figs are correct. So we have 3 sig figs to start. This one has 1, 2, 3, 4, 5 sig figs, and then this one is exact. So yes, I should have 3 sig figs. And now let's convert our 1,300 kilometers, and we need to go to miles. So in 1 kilometer, there are 0.62137 miles. And that gives me 810 miles. Now let's make sure of my sig figs. This 1,300 here has 2, just like the problem told us. Of course, this conversion factor is 1, 2, 3, 4, 5, so I should have 2 sig figs in my answer. And you can see, yes, I have 2 significant figures in my answer. So now to get the miles per gallon, I am going to take my 810 miles divided by my 15.8 gallons, and I get 51 miles per gallon. Let's again check our sig figs. So my numerator has 2 sig figs, my denominator has 3, so my answer should have 2 sig figs, and yes, it has 2 sig figs. Now let's show this in 1 step instead of 2. So if I were to take my 1,300 kilometers over my 59.7 liters, let's convert into the units we want. So first I'm going to convert my kilometers into miles. Again, if you wanted to, you could convert your liters into gallons first. It does not make a difference. So in 1 kilometer, I have 0.62137 miles. And now I'm going to take care of my liters here. So in 1 liter, there are 1.0567 quarts. And of course, there are 4 quarts in 1 gallon. Okay, so this also, when I do this calculation, gives me 51 miles per gallon, which is exactly what I got up here. But let's just make sure of my cancellation. So you can see how my kilometers canceled, my liters canceled, and my quarts canceled. So I was left with miles in the numerator and gallons in the denominator, which is exactly what I wanted. Now in terms of sig figs, my 1300 has 2 sig figs. My 59.7 has 3. This conversion factor has 1, 2, 3, 4, 5 sig figs. This one also has 5 sig figs. And of course, this is an exact conversion. So I am limited by my 1300 kilometers with just 2 sig figs. So my answer should have 2 sig figs. Now let's tackle part B. So part B up here, we are given the cost per gallon and we want the fuel cost for this trip. This is where breaking it up into 2 sections helps because I already have my gallons. So I know I used 15.8 gallons and the cost here is $3.90 per gallon. And so that gives me a total cost of $61.60. Now let's check our sig figs here. So we started with 15.8 gallons. Again, that is from this calculation up here that has 3 sig figs. Our cost per gallon here also has 3 sig figs. This 0 here is significant. So I should have 3 sig figs in my answer, which I do right here. Now usually when we report money, we report it to 2 decimal places always. So you might also see $61.60 written like this. Example 1.11. We are going to convert from Celsius. Normal body temperature has been commonly accepted as 37 degrees Celsius, although it varies depending on time of day and method of measurement as well as among individuals. What is this temperature on the Kelvin scale and on the Fahrenheit scale? So we are going to convert Celsius to Kelvin and to Fahrenheit. So let's start with Kelvin. So Kelvin is 273.15 plus our degrees Celsius. So in our case, what we're going to have is plus 37.0, and that is going to give us Kelvin as 310.2. Okay, so why did I round to just 1 decimal place here? That is because we're doing addition subtraction, so I need to look at the number that has the fewest decimal places, and that is this 37.0, which is why I only have 1 decimal place in the answer. Now let's convert to Fahrenheit. So my calculation for degrees Fahrenheit is going to be 9/5 times my degrees Celsius plus 32.0. So I'm going to take 9/5 of 37.0 and add 32.0. And that gives me a degrees Fahrenheit of 98.6. Okay, so let's double check sig figs. This 9/5 is considered an exact conversion. So I should have 3 sig figs here, 1, 2, 3. And of course, now I'm doing addition subtraction, so I'm limited by my decimal places. They each have 1 decimal place, so my answer should have 1 decimal place. Now for the check your learning. We are going to convert 80.92 Celsius to Kelvin and Fahrenheit again. So starting with Kelvin, we are going to take 273.15 and we're going to add our degrees Celsius. So let's put in our degrees Celsius That is 80.92. And so our Kelvin is going to be 354.07. All right, so notice we're doing addition. So I'm looking at decimal places. Each of these have 2 decimal places, so my answer also has 2 decimal places. Now let's convert it into Fahrenheit. So Fahrenheit is 9/5 of what my Celsius is plus 32.0. Okay, so that is going to be 9/5 of 80.92 plus 32.0. So that is going to give me a degrees Fahrenheit of 177.7. All right, so sig figs. This 80.92 has 4 sig figs. Remember, this is exact, so I'm going to have 4 sig figs. That answer, if you're curious, is actually 145.7. Now I'm going to do addition subtraction. And so I'm looking at decimal places. So I have 1 decimal place here, 1 decimal place here, which gives me 1 decimal place in my answer. So sometimes, especially with these mixed operations, it can be helpful to do the intermediate step, just kind of either as a side calculation. You can see I just wrote it above in a different color. Example 1.12, conversion from Fahrenheit. Baking a ready-made pizza calls for an oven temperature of 450 degrees Fahrenheit. If you're in Europe and your oven thermometer uses the Celsius scale, what is the setting? And then what is the Kelvin temperature as well? So we're going to take Fahrenheit, we're going to convert to Celsius, and then we're going to convert to Kelvin. Okay, so let's first convert to Celsius. So that is going to be 5/9 times my degrees Fahrenheit minus 32. So that is going to be 5/9 times 450 minus 32. All right, so my sig figs here are going to be limited by my decimal places. So I have 1 decimal place here, and actually this 0 is not significant, so I'm limited to the tens place here. So when I get my degrees Celsius, I need to round to the tens place, and that will give me 230 degrees Celsius. Okay, let's do Kelvin. So Kelvin is going to be 273.15 plus our degrees Celsius. So that is going to be 273.15 plus, again, our 230, which we just calculated. And that gives us a Kelvin of 503, except we need to check sig figs. Remember, this number right here is rounded to the tens place. So we need to round here to the tens place. But we don't want to actually say 500 because that's actually rounded to the hundreds place. So what we really want to do is we want to use scientific notation and call this 5.0 times 10 to the second Kelvin. This is just one of those examples where it gets awkward to write things in standard notation. It's much better to go to scientific notation. Okay, now let's do a check your learning. Convert 50 degrees Fahrenheit to degrees Celsius and Kelvin. So let's first convert to degrees Celsius. That is going to be 5/9 times degrees Fahrenheit minus 32.0. So that is going to be 5/9 of 50 minus 32.0. Again, this 50 is rounded to the tens place, so my degrees Celsius also needs to be rounded to the tens place. So that is going to give me 10 degrees Celsius. Okay, now let's do Kelvin, and that is 273.15 plus degrees Celsius. So that's going to be 273.15 plus 10. Remember, this is rounded to the tens place. So my Kelvin is going to be 280. And those are all of the example problems in Chapter 1.